Hello, and welcome to section 5 of our Python journey. In this section, we're stepping into one of the most useful topics in programming, data structures. Up to now, you've been working with single variables, conditions, and loops. Today, we open a new door, how to store and organize many values together using lists and tuples. Think of this as the moment your programs grow from holding one thing to handling whole collection of things like shopping lists, sensor readings, or student marks. Take your time with this section. It's a foundation you'll use in almost every program from here on. Let's start by looking at what you'll be able to do by the end. Let's set our destination before we start the journey. By the end of this section, you should be able to do 6 things. First, you'll understand what collections mean in Python, a fancy word for containers that hold many values. Second, you'll know how to create lists from scratch. Third, you'll be able to reach into a list, pull out a single value, slice off a chunk, or change what's inside. Fourth, you will know the most common list methods, small built-in actions like append and remove. Then you'll meet tuples, the quieter cousin of lists. And sixth, and this is like the most practical skill, so you'll be able to look at a problem and decide which structure fits best. Don't worry if they sound abstract right now. We'll build each one with examples. So why bother learning data structures at all? Imagine I asked you to keep track of the temperature in your room. Just once a day. Easy. One variable, one number. Now imagine I ask you to keep track of the temperature every hour for a week. That's 168 numbers. Are you going to create 168 variables? Of course not. Your code would become unreadable. This is the moment we reach for a data structure. A data structure is simply a way to group related values together under one name. Look at the 4 examples on the screen. Student marks, shopping items, daily temperatures, and energy readings. They all have one thing in common, many values that belong together. Lists and tuples are the simplest, most common tools for this job in Python. Let me give you this analogy I use with every new student. A list in Python is just like a list you'd write on paper. Think of your shopping list: bread, milk, eggs, apples, coffee. It has many items. They're in a particular order, and you can add or cross things off. That's exactly what a Python list is. The same idea covers an attendance sheet for a class, a record of daily temperatures, or a checklist of tasks for the day. So whenever you find yourself thinking, I need to keep track of several related things, your instinct would be, that's a list. Hold this picture in your mind. Whenever the code gets abstract later, come back to the shopping list. Here's the mental shift I want you to make today. Up until now, every variable you've created held exactly one value, one number, one piece of text, one boolean. On the left side of the screen, that's the world you've been living in. Mark equals 80, right? One name, one value. On the right side is the new world we're entering. A single variable name can now hold many values at once. Marks are having 3 values, 80, 75, and 90. 3 numbers, 1 variable. This isn't a small change, it's a powerful upgrade. Almost every real program, websites, games, data analysis, even a simple weather app relies on this idea. Once you see it, you'll never want to go back to 10 separate variables. Let me show you the pain point that makes lists necessary. Imagine I'm teaching a small class and I want to store 5 student marks. Without list, I'd end up writing mark 1, 80, mark 2, 75, and so on all the way down. 5 variables, it works, but look how repetitive it is. Now imagine the class has 50 students or 500. You'd be writing variable names forever, and anytime you wanted to do something like find the highest mark, you'd have to compare each one by name. There's no way to loop through them, no way to scale up. This is what programmers call code smell. When the structure tells you something's wrong, even though it technically works. The solution would be to create a list. Look at the difference. The 5 variable mess from the previous code just collapsed into one beautiful line. Marks equals 80, 75, 90, 60, 85. The square brackets are Python's way of saying, this is a list, and here are the items in it, separated by commas. Notice 3 things. First, it reads naturally. Even a non-programmer can guess what's happening. Second, it's now ready to be looped through, sorted, totaled, searched. Third, and this is the magic, if I wanted 500 marks instead of 5, the structure of the code wouldn't change at all. That's what good data structures do. They handle one item or a million items with the same shape. A single idea will unlock most of what we do today. Let me sum up why we care about data structures with 4 points. 1, they group related data. 2, they let you access any individual value easily by its position, without inventing dozens of variable names. 3, and this is huge, they work hand in hand with loops. So you can perform the same action on every item with just a few lines of code. And 4, the cumulative effect of all this is cleaner programs. Less repetition means fewer chances to misstep something, fewer bugs, easier maintenance. If you remember nothing else from this slide, remember this. Lists make your code shorter, clearer, and more powerful at the same time. There are several data structures in Python: lists, tuples, dictionaries, sets, and more. But this section we focus on the 2 simplest and most common, lists and tuples. Lists written with square brackets are changeable. That means after you create one, you can add to it, remove from it, or modify items inside. Tuples, written with round brackets, are fixed. Once you create one, its contents are locked. That difference may seem small, but it has a big impact on when you choose each. Think of lists as your everyday workhorse, and tuples as a safe locker for things that shouldn't change. We'll spend most of today on lists and meet tuples in the second half. Here's a comparison. Lists can change, tuples usually do not change. That one sentence captures the most important practical difference. Think about daily readings, sensor values that come in hour after hour. The list grows. You keep adding new readings. That's a perfect job for a list. Now think about the coordinates of a room, a latitude and longitude. Those numbers do not change. The room isn't going anywhere. That's like a perfect job for a tuple. Even though both can store a collection of values, choosing the right one signals your intent to anyone reading the code. A tuple shouts, this data is fixed, don't touch it. And Python enforces that for you. Now let's nail down the definition. A list in Python is an ordered collection of values. Every word in that phrase matters. Collection, it holds many values. Ordered means those values have a fixed sequence. The first item stays the first item, the second stays the second, and so on. And values, what's inside, can be almost anything: numbers, text, even booleans. 3 rules to remember about the syntax. Lists always sit inside square brackets. Items are separated by commas, and you can mix data types freely. On the right, you see a simple list of 3 strings: bread, milk, eggs. The brackets open it, the commas separate it, and the closing bracket finishes it. That's the entire grammar. Time to write your first real list together. This is a code editor slide. Everything you see on the dark panel is Python code you could type into any editor. Let's read it line by line first. Line 1, numbers. We are having 1, 2, 3, 4 in square brackets. On the left side of the equal sign is the variable name, numbers. On the right side, the square brackets is opening a list, and inside we're putting 4 integers separated by commas. The whole list, all 4 values, is now stored under the single name, numbers. Line 2 is print, then parenthesis, numbers. The built-in print function takes whatever is in the parentheses and displays it. So we're telling Python, show me what's inside the numbers list. Let's see what the results are on the next slide. Here's the result. So the $sign you see is the command prompt. That's where you type the command to run your file. We type python numbers.py and press enter. Python reads the file from top to bottom. It creates the lists on line 1. Then on line 2, it prints the list. The output appears on the next line, this 1, 2, 3, 4 in brackets. Notice how Python displays the list in the same shape we wrote it? The square brackets, the items separated by commas. That's not an accident. It's Python's way of showing you, yes, this, you instantly can see this is a list. If you ever print a variable and see brackets like this, you know it's typed. A small observation is that, and also a habit professional programmers rely on every day. Here's something that surprises students coming from other languages. In Python, a list doesn't have to contain just one type of value. You can mix and match. A single list could contain a whole number, a piece of text, a decimal number, and a true or false value altogether. The 4 data types on this slide are the ones you've already met. Integers like 1, strings like Python in double quotes, floats like 3.5, and booleans like true. Now, just because you can mix types doesn't always mean you should. In practice, most lists hold one kind of thing, all marks, all temperatures, all names, but the flexibility is there when you need it. For example, when storing a row from a spreadsheet that has a name, a score, a percentage, and a pass or fail flag. Let's see mix types in action. On line 1, we create a variable called data and store a list with 4 different things inside. The first item 1 is an integer. The second Python is a string in the quotes. The third 3.5 is a float, and the fourth is true, which is a boolean with a capital T. The capital letter matters in Python, remember. All 4 sit happily side by side inside the same set of square brackets. Then line 2 prints the list. Pay attention to how the syntax doesn't change just because the data types differ. Same brackets. Same commas. Python is comfortable with this. You should be too. Here's the output of our mixed list. We type the string in double quotes Python, but when Python prints the list, it shows it in single quotes. Python. Don't let that confuse you. In Python, single and double quotes are completely interchangeable for strings. The language picks one when displaying. The important part is that all 4 values appear inside the brackets, in the same order we wrote them, separated by commas. Python preserved the order of the items and kept their original types intact. This is your proof that a single list really can carry an integer, a string, a float, and a boolean side by side without any problem. Now let's move on to one of the most important list skills, accessing individual items. Now we move from creating lists to using them. The first skill is indexing. Reaching in and grabbing a specific item is basically indexing. Every item in list has a position, and we call that position the index. Here's the part that catches almost every beginner. Python starts counting from 0, not from 1. So in this list of 5 values, the first item 10 is at index 0. The second item 20 is at index 1, and so on. The last item 50 is at index 4, not 5. This zero-based counting feels strange at first, but that's standard across nearly every programming language. The trick is to read index as how many steps from the start. The first item is 0 steps from the start. Practice this until it feels very natural. Now let's grab specific item from a list now. Line 1 creates a list called numbers with three values 10, 20, and 30. Line 2 uses the indexing syntax, the variable name followed by square brackets with the index number inside. So numbers in bracket 0 means give me the item at position 0, which is 10. Line 3 is asking for numbers in square brackets 2, which is the item at position 2, which is 30. Watch out. The brackets on line 1 create the list, but the brackets on lines 2 and 3 are doing something different. They are telling you that they're indexing into an existing list. Same symbol, two rows. Context tells you which. So let's run it. And here's the output. Two print statements produce two lines, 10 and 30. The first line comes from numbers 0, which pulled out the first item. The second line comes from numbers 2 in the square brackets, which pulled out the third item. Notice we skipped index 1, so 20 doesn't appear in the output at all. This is exactly how you'd access individual values in real program. For example, pulling the first temperature reading of the day, or the third student's mark from a list of marks. The shape list name in a square bracket position is one of the most common patterns you'll ever write in Python. Lock it into muscle memory. This is the single most common mistake new Python learners make, so let's confront it head on. If your list has three items, the valid indexes are 0, 1, and 2. Index 3 does not exist. Many beginners think three items, so the last one is index 3, and that's wrong. The last index is always length minus 1. If you do try to access an index that's too big, Python will stop your program with a red error message called an index error. You can see it on the screen and it says list index out of range. That message is Python's polite way of saying you asked for an item that doesn't exist. Whenever you see this error in your own code, count your items and remember the last index is 1 less than the count. Indexing pulls out one item, slicing pulls out a range of items. The syntax uses square brackets again. But now we put two numbers inside, separated by a colon. The first number is where to start. The second number is where to stop. But here's the twist that trips everyone up at first. The stop position is not included in the result. So numbers 1 is to 4 means starting at index 1 and stopping just before index 4. You get indexes 1, 2, and 3, but not 4. I know this feels weird. The Python designers chose this rule so that the total count of items you get in is simply stop minus start, which makes loops and pagination easier to write. Keep telling yourself start is included, stop is excluded. Let's slice. Line 1 creates a list of 5 numbers, 1 through 5. Line 2 asks Python to print a slice. Numbers 1 is to 4. Reading this aloud from index 1 up to but not including index 4. So, index 1 is the value 2. Index 4 is the value 5. But we stop before that. So 5 is not included. We expect 3 values 2, 3, and 4. Notice another nice pattern here. The number of items returned is a stop minus start. That's 4 minus 1, which is 3 items. That little arithmetic shortcut becomes very handy when you're slicing the big lists. This is the result, 2, 3, 4. 3 items, exactly as we predicted. Notice that Python returns a new list, square brackets, commas, not just a single value. Even if your slice contains only one item, the result is still a list. The original list numbers hasn't changed at all. We just looked at a portion of it. We didn't remove anything. This is a really important property. Slicing is read-only operation from the original list's point of view. If you want to keep working with the slice, you can save it in your own variable, like middle equals numbers, then put 1 is to 4. Now middle holds those 3 values and numbers will be still intact. Let's walk through that slice one more time. Slowly now. With the picture, we have a list of 5 values, 1, 2, 3, 4, 5. The indexes underneath are 0, 1, 2, 3, and 4. When we write numbers 1 is to 4, step 1 is that we start at index 1, which holds the value 2. That's the first item in our slice. Step 2, we stop before index 4, meaning we never reach index 4. Step 3, we collect everything in between, indexes 1, 2, and 3, which are values 2, 3, and 4. The result is the list 2, 3, and 4 in square brackets. If this still feels strange, try drawing your own list on paper next time you slice. Within 2 or 3 exercises, it will click and feel completely natural. Now let me introduce you to a new word, mutable. In everyday English, we don't use this word much, but in programming, it just means able to be changed. Lists in Python are mutable. That means once you've created a list, you don't have to throw it away. If you want to change something, you can update an item in place and add new items or remove existing ones, all without creating a fresh list. This is one of the main reasons lists are so popular. They're flexible. If you've got a sensor that reports a new reading every minute, you can keep updating the same list rather than rebuilding it from scratch every time. Tuples, which we'll meet later, are the opposite. They're immutable, meaning once made, they're locked. Let's see mutability in action. Line 1 creates a list of 3 numbers, 1, 2, and 3. Line 2 does something we haven't done before. It puts number 0 on the left of the equal sign. When indexing appears on the left of an assignment, Python doesn't read the value there, it replaces it. So number in square bracket 0 equals 10 means go to position 0 in the list and put 10 in there instead. The 1 that used to live in that slot is gone now. Line 3 prints the updated list. Watch what happens. We expect to see 10 in the first position now, followed by 2 and 3, unchanged. This is the core pattern for editing a list, and it's exactly how you would update a single field in a database row, or correct one wrong value in a dataset. Here's the proof. The output is 10, 2, 3 in square brackets. The value at index 0 has been replaced. It used to be now a 1, and now it's 10. The other two values, 2 and 3, are exactly where we left them. Two things to notice here. First, this is still the same list. We didn't make a new one. We edited the existing one in place. Second, only one position changed. The rest of the list was untouched. That's a really useful property in real applications. Imagine a class list where one student changes their name. You don't want to rebuild the whole list. You just want to fix that one row. That's exactly what list mutability gives you. Updating a value is one thing, but what if you want the list to grow? That's where the append method comes in. Append just means add to the end. The syntax is new for us. You write the list name, then a dot, and the word append, then parentheses with a new value inside. So numbers dot append in parentheses 3 takes a list called numbers and adds 3 to the very end of it. While we're here, let me introduce you to a new term called method. A method is just an action that belongs to a value. Lists have methods, strings have methods, numbers have methods. You call them with a dot. Whenever you see a dot followed by a word and parentheses, that's a method being called. Let's run append. Line 1 creates a list with 2 items, 1 and 2. Line 2 calls the append method on that list, numbers.append in parentheses 3. Now try to read it like a sentence. Numbers, please append 3. This adds 3 to the end of the list. Notice we don't write numbers equals numbers.append 3. That would actually break things. Append modifies the list in place. It doesn't return a new list. That's a really common beginner trap. So commit it to memory. Just numbers.append in parentheses 3. Nothing on the left. Line 3 then prints the result. Watch what happens to the size of the list. Perfect. The output is, in square brackets, 1, 2, 3. We started with 2 items and ended with 3. That's a new value. 3 is sitting at the end of the list, just as the name append promised. This pattern, called append with a single value, is the most common way to build up a list as your program runs. For example, in a loop that reads sensor data once per minute, you might call readings.append in parentheses new value every minute, and over an hour your list grows from empty to 60 values. Append is your everyday tool for growing collections. Now let's call remove. So we can add to a list, but we can also take things out. Python gives two main ways to do that, and they work differently. The first is remove. You pass it a value and it deletes the first item in the list that matches the value. So numbers that remove in parentheses 2 looks through the list and finds 2 and removes it. The second is pop. You don't give it a value, you just call it with empty parentheses and it removes the last item, whatever that happens to be. The simplest way to keep this straight is that remove by value, pop from the end. Both modify the list in place, just like append did. Let's see each one running. And now, here it is. Line 1 creates the familiar list of 1, 2, 3. Line 2 checks, like, does the work numbers.remove in parentheses 2. Now try reading it like a request. Numbers, please remove the value 2. Python scans the list from the start, finds 2, and deletes it. One important detail, you give it the value you want. Gone, not the index. If you accidentally call numbers that remove in parentheses 0, thinking it removes the item at position 0, you'll actually be telling Python to find the value 10, and if there is no 0 in the list, you'll get an error. Line 3 prints the result so we can confirm what happened. And there it is. The output is 1 and 3. The 2 is gone. Notice something subtle and powerful here. When you remove an item from the middle of a list, Python automatically shifts the remaining items to close the gap. There's no empty hole left where the 2 used to be. So the list went from length 3 to length 2, and the indexes were renumbered. 1 is still at index 0, but 3 has moved from 2 to index 1. This automatic compaction is one of the conveniences of lists. You never have to think about gaps. Now let's see the other removal method, pop. Popping the last item. The first line is the same, a list of 3 numbers. Line 2 calls the numbers.pop, then parentheses. Notice the empty parentheses? We don't tell pop anything. It already knows what to do. Remove the item at the end. So the 3 disappears. Pop is great when you don't care what the last item is. You just want to drop it. For example, undoing the most recent action, or processing items one at a time from the end of a stack. Like the others, pop modifies the list in place. So we just call it directly and then print to see the result. The output is, in square brackets, 1, 2. The 3, which was at the end of the list, has been removed. Now compare this to the previous example with remove. When we used remove with the value 2, we lost an item from the middle. With pop, we lost the item at the end. Same idea, taking something out, but a different rule for choosing what goes. Quick tip you'll discover later, pop can also return the value it removed, so you can capture it in a variable, like last equals numbers of pop and then parentheses. That's useful when you want to know what was removed, not just that it was removed. But for today, just remember the simple form. Let's gather everything into one reference slide here, the most useful list operations you'll meet early on. So the 3 light cards on the top are all methods. You call them with a dot after the list name. Append adds an item, remove takes one out by value, and pop takes the last one out. The 3 dark cards below are built-in functions, len, max, and min. They have a slightly different shape. You wrap them around the list, like len, then parentheses inside it, numbers, or max, then parentheses, numbers with no dot. Let len counts how many items are in the list, max finds the largest value, and min the smallest. So 6 operations total. With these 6, you can already write surprisingly useful programs. Keep this slide as a cheat sheet. You already know for loops from earlier sections. Here's the great news: for loops and lists are made for each other. When you put in a list inside a for loop, Python automatically walks through every item one at a time, from the first to the last. On the left of the slide, you see the list itself, 3 numbers, 10, 20, and 30. On the right is what the loop does. Take each item in turn, then do something with it, repeat until the list is finished, and then move on. There's no need to write any index numbers, no need to know the length in advance. Python handles all of that. This is what makes lists so powerful. You can write code for one item and Python applies it to every item. Here's the classic for loop pattern. Line 1 creates a list of 3 numbers. Line 3 is the loop header for n in numbers. Let's break it down word by word. For says start a loop, n is a temporary variable name. Now I could have called it anything, item X or valued, all work. In numbers tells Python which list to walk through. The colon at the end opens the loop body, then on line 4, indented with 4 spaces, is what we want to do with each item. Print it. The indentation is what tells Python this line belongs to the loop. On the first pass, n becomes 1, and on the second, 2, and on the third, 3. Let's see it run. And here's the output, 1, 2, 3, each number printed on its own line. The print statement ran 3 times, once per item. This is the real superpower of lists and loops together. You wrote one print statement, but it acted on every item. If your list had 1,000 numbers, the code wouldn't change at all. You just see 1,000 lines of output. This is what programmers mean when they say code scales. The same handful of lines does more work as the data grows. Take a moment and appreciate how much we just accomplished with 4 lines of code. Up to now, every time we looped through a list, we just printed the items. But the real value of loops is that you can do any work on each item, not just print it. The most common pattern is what programmers call accumulation, building up a result as the loop progresses. The classic example is adding all the items in a list to find total. We start with a total of 0. Then for each number in the list, we add it to the total. By the end of the loop, total holds the sum of every item. We don't have to write 3 separate addition statements. We just let the loop do it. Let's see this in code. Here's the accumulation pattern in real Python. Line 1 is creating a list and putting those values inside that list numbers. And then we are setting the total to 0. That's the starting point. Line 4 is our familiar for loop. Line 5 is indented inside the loop, is the magic. Total plus equals n. This little operator plus equals means add the right side to the left side and store it back. So on the first pass, total goes from 0 to 1. On the second pass, 1 to 3. On the third, from 3 to 6. After the loop finishes, line 7 prints the final total. Trace through this with me on paper if you can. That's the best way to really feel how a loop accumulates a result. So it was 6. That's the sum of 1, 2, and 3. The loop ran 3 times, and each time it added one more number to the running total. You can imagine the journey. 0 plus 1 is 1, plus 2 is 3, plus 3 is 6. This accumulation pattern is one of the most useful things you'll ever learn. Replace add with multiply and you have product. Replace it with count and you have a counter. Replace it with compare to the maximum so far and you have a way to find the largest value yourself. Once you internalize the pattern of starting with a value, looping and updating it, a huge range of problems opens up. Let's give you a real-world scenario where everything we've learned comes together. Imagine a smart meter in a home or office. Every few hours, it records how much energy was used. You end up with a sequence of numbers. 120 units in the morning, 150 in the mid-morning, 180 at noon, 200 in the afternoon. That's a perfect job for a list. Each atom is one reading, and the order matters because it represents time. We can store it as energy equals in square brackets 120, 150, 180, and 200. From there, the questions naturally flow. When was the usage highest, lowest? What was the average? How does today compare to yesterday? With lists and a few simple operations, you can answer all of those. Let's solve our real problem in 3 lines. Line 1 creates our energy readings list. Line 3 uses the built-in functions max wrapped around the list to find the largest value. The result is stored in a new variable called peak. Notice that max is one of those built-in functions we mentioned earlier. No dot, just max and parenthesis energy. Line 4 prints a friendly label along with the value. The comma inside the print tells Python to separate the two pieces with a space when displaying. So the output won't just be a bare number, it'll have context. That is what we mean when we say data structures and built-in functions work together. A single function call replaces what would have been an entire loop. Now output is peak energy then 200. The 200 reading was the highest of the 4. The label peak energy came from the string in our print statement, and Python added a space before printing the value. Notice how readable that line is? Even somebody who doesn't know Python can roughly understand what's happening. This is the practical payoff of all the small things we've learned today. Real questions like what was the highest reading can be answered with just a few lines of code. Try this on your own with a list of student marks, sensor temperatures, or even daily sales figures. Same pattern, same handful of functions. So far, each list has simple values, numbers, strings, booleans, but here is a powerful twist. A list can contain another list. We call it a nested list. Why would we want that? Because a single flat list is one-dimensional, like a row of values. A nested list is two-dimensional, like a grid. You can think of the outer as a stack of rows and each inner list as open row of values. That's why nested lists are perfect for tables, spreadsheets, game boards, or any data with rows and columns. On the right of the slide, the outer brackets hold two inner lists, one by one, just one by one. And on the right side, the outer brackets are holding the two inner lists, one for row 1 and one for row 2. Together, they form a tiny 2 by 2 grid. Let's reach into a nested list. So line 1 is creating our matrix. The outer brackets hold two inner lists. Line 2 uses something new, two index brackets in a row. Matrix, then one square bracket with 0 and one square bracket with 1. Read that left to right. The first zero reaches into the outer list and pulls out the first inner list. That's 1, 2. Then the second one reaches into that inner list and pulls out the item in position 1, which is 2. Think of it as row first, then column. If you've ever used a spreadsheet, this is just like saying, give me a row 1 and column 2. 2 square brackets, 2 steps, 1 value. The output is simply 2. Let's retrace the path Python took. First, it looked at the matrix, which has 2 inner lists. It picked the list 1 at index 0. That's 1, 2. Then from that inner list, it picked the item at index 1, which is the value 2. 2 hops, 1 final answer. The pattern of double indexing scales up. You can have lists nested even deeper, with 3 or 4 levels. But in practice, 2 levels is the most common, because that maps so neatly onto rows and columns. Next, let's see this idea in real scenario, monitoring temperatures across multiple rooms. Let's give nested lists a purpose. Imagine you're monitoring 2 rooms, room A and room B, and you record the temperature at 3 different times during the day. There's 2 rooms, each with 3 readings, a perfect 2 by 3 table. As a nested list, the outer list has 2 items, and each item is itself a list of 3 temperatures. Row 1 captures room A's day, row 2 captures room B's day. Once it's stored this way, you can ask precise questions like, what was room B's reading at 3 p.m.? Using 2 index numbers. This is the kind of structure you'd actually meet in a small monitoring system or simple inventory program. Let's read a value from our room 2 table, our 2-room table. Lines 1 to 4 set up the nested list. Notice we've spread it across multiple lines to make it readable. Python is happy with that as long as the brackets and comments line up. The outer list temps contains 2 inner lists. The first holds room A's 3 readings, and the second holds room B's. Then on line 7, we put temps, then first square bracket 1, and then second square bracket 2. First index 1 picks the second row. So that's room B, and second index 2 picks the third reading in that row. Together room B at the third time point. So reading nested indexes always work the same way. Outer first, inner most second. Let's confirm. The output is 30, which is exactly the value at room B's third time point on the table we drew earlier. We pinpointed one cell in a 2-dimensional grid with just 2 index numbers. Imagine extending this idea, a building with 50 rooms, each with 24 hourly readings. The structure stays the same, only the numbers grow. That's why nested lists are such an important stepping stone. They're your first taste of working with structured tabular data, the kind that feels spreadsheets, dashboards, and reports in real life. Now let's pivot to our second main topic, tuples. Time to meet tuples, the second data structure of this section. A tuple is almost identical to a list in many ways. It holds many values in order and you can index into it. But here's one big difference. Once you create a tuple, you cannot change it. You can't add to it, you can't remove it from it, and you can't replace an item. We call this property immutability, which is just a fancy word for unchangeable. Tuples are written with round brackets instead of square ones. and the items inside it are still separated by commas. The little padlock icon on the right is how I want you to picture it. A tuple is a data that's locked in. Let's create a first tuple. Line 1 stores a tuple of two decimal numbers, 3.1 and 101.6. Under the name location, notice the round brackets. That's the visible difference from a list. Inside, two values separated by comma, just as before. We picked a pair of numbers that could represent a real-world location, latitude 3.1 and longitude 101.6, which is roughly Kuala Lumpur. Locations don't move, so a tuple is the right fit. Line 2 prints the tuple. The code looks almost identical to a list, but Python is treating this differently behind the scenes. And the next slide will show how the print output reflects that. Look at the output, 3.1 and 101.6. Same numbers, but the brackets are round, not square. This is Python's way of telling you I'm a tuple, not a list. That's a great little debugging trick. Anytime you print a variable and you want to know whether it's a list or a tuple, the bracket shape gives you the answer instantly. Square brackets mean list, round brackets mean tuple. We've now created both types of containers and printed them. And the visible differences comes from down to those brackets. Behind the scenes, though, Python treats them very differently when it comes to changes. When should you actually reach for a tuple instead of a list? The rule of thumb is use a tuple when the values shouldn't change for the lifetime of the program. Look at the four examples on the screen. Room coordinates, latitude and longitude, don't change. A sensor's mounted location, building, room, floor doesn't change once installed. System configuration settings doesn't change once installed. Our loaded system configuration settings would also are loaded once the program starts. Usually shouldn't be modified mid-run. A building ID paired with a zone code, fixed labels also wouldn't change. In each case, choosing a tuple does two helpful things. It tells other people reading the code this data is meant to stay fixed, and it stops you from accidentally changing it. It's a small piece of insurance built into the syntax. Here's a small but useful real-world tuple. Imagine you're modeling a battery. It has a capacity in amp hours, say 100. Chemistry, let's say lithium ion, and an efficiency factor, say 0.9, meaning 90% of stored energy is actually usable. So those three pieces of information belong together as a fixed specification. Once a battery model is defined, you wouldn't want some other part of the program to accidentally change it to a different chemistry. So we wrap them in a tuple. Notice the values have different types, an integer, a string, and a float, all packed inside one set of round brackets. Tuples support mixed types, just like lists do. The output is 100, then in single quote line and 0.9 round brackets, three values in the order we wrote them, each in its original type. Notice Python again displays the string in single quotes even though we wrote it in double quotes, and the number 100 stays as a whole number while 0.9 is shown as a decimal. The tuple kept everything together as one unit. If somewhere later in the program you try to do something like battery underscore config, then in square brackets 1 equals NIMH to swap the chemistry, Python would refuse with an error. The tuple is locked. The refusal is a feature, not a flaw. It protects fixed data from accidental changes. Now let's bring lists and tuples together in one clear decision rule. Use a list when the data may change. Daily sensor readings, student marks, a to-do list, all of these grow, shrink, or update over time. Lists are designed for that. Use a tuple when the data should stay fixed, a location, a configuration, an ID. These shouldn't be modified once set. The rule isn't about how the data looks, it's about how the data behaves. Both can store the same values. The difference is whether change is allowed. When you're writing your own programs, pause for 1 second and ask, will this data change? The single question tells you which to use. Now it's your turn to put together everything. Don't just watch me code, try this yourself. Step 1. Create a list of 5 energy readings. Make up your own values. Step 2. Use the max function to find the highest reading and print it. Step 3. Use min for the lowest. Step 4. Use len to print out how many readings you have. Each step is just 1 or 2 lines of code, and you've seen all the building blocks in this lesson. Pause the video, open up your editor, and give it a try. If you get stuck, go back to the energy scenario slides. The code there is almost identical. Mistakes are part of learning. Embrace the error messages, read them carefully, and they'll show you the way. Let's bring it all together. In this section, we learned 6 big ideas. 1. Lists store many values under a single name. 2. Lists are mutable. You can change them after creation. 3. Lists pair perfectly with for loops, letting you do work on every item with just a few lines of code. 4. Nested lists let you organize data into rows and columns, like a small table. 5. Tuples are like lists but locked, perfect for fixed information that doesn't change. And 6. The most practical skill of all, knowing when to use which makes your code clearer and safer. Well done for sticking with me through the whole section. In the next section, we'll meet 2 more powerful data structures, dictionaries and sets. See you there.